Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, plus 1, plus 2, plus 3, plus 4, 5, 6, 7, 8, 9, plus 10 seconds,
B3 tracking, auto tracking, B2 tracking,
plus 15 seconds, plus 20 seconds, plus 25 seconds,
lift step pumps ignited,
plus 30 seconds, plus 35 seconds, plus 40 seconds,
first stage
plus 45 seconds.
So maybe in the next 50 to 60 seconds we will hear the announcement of PS3 burnout, followed by PS3 separation at a much later time.
Dr. Somnath,
ASTROSAT has been separated.
and is placed in orbit.
ASTROSAT has separation.
पृथक्करण हो चुका है, बहुत ही महत्वपूर्ण चरण.
And this is a successful separation of the Lemur 4 satellite as well.
ये था समापन एक तरह से
Congratulations to one and all.
सभी लोगों का.
Director.
ISRO has crossed yet another milestone by launching ASTROSAT today morning from Sriharikota. A PSLV rocket carried 7 satellites including ASTROSAT exactly at 10 am. It is India's first attempt at setting up an observatory in space, a place from where it can easily study cosmological phenomena. The ASTROSAT has the ability to observe celestial bodies like distant stars and cosmic X-ray sources in different wavelengths simultaneously.
Let us begin this program of Meet the Astronomers of the ASTROSAT by congratulating ourselves. All Indians need to be congratulated because for the first time we have a very successful space observatory which is our own, the ASTROSAT.
Today, many artificial satellites built in India are circling the Earth in various orbits. Through their services, they have improved the quality of our life and made it safer. But there is one Indian satellite that is different from these space-based assets of India. Instead of using its vantage point in space to look down at the Earth, this satellite will focus its attention towards the heavens to help enhance our knowledge about the universe. This is ASTROSAT, India's first dedicated multi-wavelength orbiting astronomical laboratory. Different types of electromagnetic radiation help us understand different aspects of the universe. While infrared waves enlighten us about the dim stars as well as star and planet formation, the ultraviolet rays provide information on very hot stars. Similarly, X-rays and gamma rays provide information on extremely violent events in the universe like supernovae or the devouring of starry material by a black hole. And microwaves help us understand the formation and evolution of the universe. ASTROSAT mission envisages an Earth-orbiting scientific satellite with payloads capable of simultaneously observing the universe in the visible, ultraviolet and X-ray regions of the electromagnetic spectrum. Thus, ASTROSAT is a multi-wavelength space observatory of India. It is expected to further enhance our knowledge about many interesting processes in this universe. Once it is separated from the fourth stage of PSLV, ASTROSAT begins its independent orbital life and after a few days will be ready to begin its assigned task of observing the universe in the visible, ultraviolet and X-ray regions of the electromagnetic spectrum. The Ultraviolet Imaging Telescope UVIT is jointly developed by Indian Institute of Astrophysics at Bangalore and Inter-University Centre for Astronomy and Astrophysics at Pune, in collaboration with the Canadian Space Agency. This instrument is capable of observing the sky in the visible, near ultraviolet and far ultraviolet regions of the electromagnetic spectrum. Large Areas X-ray Proportional Counter LAXPC, the second payload of ASTROSAT, is designed to study the variations in the emission of X-rays by a type of binary stars known as X-ray binaries, as well as to study other cosmic X-ray sources. It can make measurements of the spectral features of different classes of X-ray sources over a wide spectral range. LAXPC has nearly 5 times more effective area for collecting X-ray photons with energy beyond a certain range compared to another similar scientific satellite mission from abroad. Soft X-ray Telescope SXT of ASTROSAT, developed by TIFR along with the Inter-University Centre for Astronomy and Astrophysics and University of Leicester, UK, is designed for studying the variations in the X-ray spectrum of a lower X-ray energy range emitted by distant celestial sources. This payload has a 2-meter focal length telescope with tin conical gold-coated aluminium foil mirrors. These special mirrors reflect X-rays that are incident on them at a very shallow angle. The focal plane camera of this instrument has a cooled charge-coupled device. Cadmium Zinc Telluride Imager CZTI, yet another ASTROSAT payload functioning in the X-ray region, extends the capability of the satellite to sense X-rays of high energy. This payload may also be able to detect gamma ray bursts and study their characteristics. CZTI payload is developed by TIFR in collaboration with Inter-University Centre for Astronomy and Astrophysics and ISRO. The fifth payload of ASTROSAT is the Scanning Sky Monitor SSM, developed by ISRO Satellite Centre at Bangalore, along with the Inter-University Centre for Astronomy and Astrophysics. This instrument is designed to scan the sky for long-term monitoring of bright X-ray sources. It is capable of detecting and locating objects that emit the bursts of X-rays during a very short period. Such extremely brief sources of X-rays will then be studied in detail by other instruments on ASTROSAT. ASTROSAT was realized with the participation of all the major astronomy institutions and some of the universities in India. It is the first satellite mission to be operated in India as a space observatory.
Scientists who are present here are going to tell you, enlighten you more about the details of the scientific mission, ASTROSAT. And here we have several scientists from the Indian Institute of Astrophysics. Dr. Annapurni Subramaniam, Dr. Deepankar Banerjee, Dr. Firoza Sutaria, Dr. Rakesh Mohan, Dr. Koshi George. The Astronomical Society of India is a union of all astronomers and astrophysicists of India. Its Public Outreach and Education Committee is aiming at taking astrophysics to all students and researchers at various levels across the country.
So I will not take much time here. What I have done is from the Astronomical Society of India, we just prepared a small little note. So I have few copies of that. So I will just pass it on to you. So you can use this as a ready reference. But some of my colleagues from my parent institution, that is Indian Institute of Astrophysics, are here who are directly involved with the mission. So I will request them to take your questions. If there anything with regard to Astronomical Society of India and its activities, I'll be happy to answer your queries now or later.
I am the calibration scientist for UVIT, and I'm responsible for the calibrations, combining the calibrations in ground and delivering the calibrations in orbit, which is essential to deliver science from this instrument.
So this was released at a height of 650 kilometers by PSLV. Now, this is in orbit, so at that particular height and with the velocity, it goes around the Earth. Now, after that, this is kind of folded in and it opens up. These are the solar panels which are facing the sun, so it generates energy to run this observatory. So this is basically a combination of 5 telescopes. This is basically an observatory. We call it an observatory where we have multiple things happening apart from just one telescope looking at it. So we have, this is the SSM, the scanning sky monitor, the 3 things. It'll go differently. This one will go like this one will go like this, and this one will go like this. This is scanning the sky for X-ray transients. If there's any burst in X-ray, this will be able to detect it and then tell us that there's something happening out there in X-ray. And this is a star sensor. It's a cone which senses the stars in the sky just for orientation purpose. So these 2 are the UVIT-2 telescopes. UVIT has 2 telescopes. That is the UV imaging telescope. These 2, and this is the soft X-ray telescope. This is the cadmium zinc telluride imager, and these 3 are the large X-ray proportional counter detectors. So put together, it can span a large part of the electromagnetic spectrum, right from very high energy photons, is 200 keV, up to visible length. So this is the first time where we are able to simultaneously detect photons from a large energy, very high energy photon, to a visible energy photon simultaneously. So as you can see, all this would point out to one particular location in the sky. If I turn like this, and he was turning it like this, right? So the whole telescope will turn to one particular direction. So you are sampling the energy range, right? From, it's like I'm looking at the sun, and I'm trying to see what the sun sees in X-ray, right from X-ray till visible. It'll look very different. As an example, this is the photograph you have seen here. This galaxy looks very different in various wavelengths. So why should we look at wavelengths? Is because the energy produced has different mechanisms. We don't understand why these photons are produced. So this tells you for the first time, there are many missions up in the sky which will look at either X-ray or visible or UV. So it's just like tasting one food at different places, made at different places at different times. It's not going to tell you the whole truth, right? So it's done simultaneously. This is the beauty of ASTROSAT. And why is it not being done? It's a very complicated mission. So this is the first time we have achieved it, a complicated mission to sample all the photons together.
Are the images recorded and sent to Earth immediately?
Yes. So what happens is its one orbit is 90 minutes. So it's a polar orbit. So whenever you have crossing across the signal stations, it will send down the signals. So we have a dump, every dump happening, data dump. We have a solid state recorder which records the data. Okay? And then when it comes in connection with the ground, it plays back the data. We call it the playback. When plays back, the data is dumped. And at the same contact, you also upload the signals, which is to be operated, the instruments to be operated.
Will all the cameras start working together?
So initially, we have stabilized. First thing will be to open the panels. The solar panels are open. So there's a sequence for the first 90 days by which one by one the systems will come on live. So whatever is alive, that data will be brought down. So there's a sequence of operations for each payload. So one payload comes on, then after 10 days another payload comes on, then it has to stabilize. So my instrument is going to come on 63rd day.
Will ASTROSAT observe during the daytime also?
We observe only in the night sky part. UVIT observes only in the night sky part. We don't observe in the sun time part. Yeah, but the other payloads have only the night sky, but the UVIT. But the other payloads can observe during the daytime. But that time the UVIT will have a block.
How will you avoid the sun?
There is a minimum sun avoidance is required, where it will not be directly shown onto the mirror, UV mirror. This is the challenge, because when you have all the wavelengths to be observed together, so you cannot have all the conditions which is coming from one payload will affect the other payloads also. So we have minimum sun avoidance, moon avoidance, And only within that, in the night sky only, UV will observe.
Will the images be made available to all?
So you see, generally, any mission will have its own internal policies in terms of the data, rights. So what Annapurni just now mentioned, the astronomy community has come to this conclusion. There will be a sort of 6 months to 1 year period for the data rights with the observer. So as she pointed out, once the data, or the telescope is available for accepting new proposals, so the scientist will be allowed to submit a proposal, and then based on that proposal, data will be collected, and initially the data will be given to that particular scientist or group of scientists. But that also has a locking period of 6 months or 1 year. So that depends on, the policy decisions by the community. Right, so each mission has its own kind of policies. If it is a sort of other mission, it may have some different policy. But typically it's not more than 1.5 years, I would say. After that, the data becomes public and anybody can download. So essentially what will also happen is the data is, what I understand is, will be downloaded into SRAC in the ISRO center. And from there, directly the data will go to individual institutions who are hosting this data and the major scientists. So they will host the data, and eventually it will be made public after that lock-in period of, say, whatever, 1.5 years or so.
How is ASTROSAT different from Chandrayaan or Mangalyaan?
Chandrayaan mission and Mangalyaan mission are planetary missions. They are meant to explore from a certain altitude the nature, the surface, the topology, and certain other properties of the planets. ASTROSAT is not a planetary mission. It's basically a stellar, galactic, extragalactic mission. It will be investigating the properties of stars, which our closest star is Sun, but our other nearest stars start off from something like 4 light years away or so. So ASTROSAT's realm, you might say, starts from about 4 light years or so.
Will you get only UV images or optical also?
Then it opens up. So one tube sees collects the FUV photons. The other one collects both near UV and visual. Now what is this far and near and everything? So why don't you just call it as UV? So it's just that if you look at the wavelength coverage, this wavelength coverage is very large. So we have this problem of photons are there, but how do you collect it? Your mobile phone has a camera. Can it collect UV photons? Can it collect X-ray photons? Can it collect infrared? No, it cannot. It works only for a specific range of energy of the photon. That is the property of the detector it detects. So you need to replace your camera if you want to see the infrared. You replace the camera if you want to see the UV. That basically means that you need different techniques to detect this. So that is why these instruments are of different sizes and shapes, right? So they're not looking similar. They have different sizes and shapes and capabilities. That's because you need different techniques to attack these or collect these photons. So one has FUV far apart of the UV where the energy is more. If you show the X-ray hand to the X-ray, what happens? The X-ray goes through it, right? But if you look at if you show your hand to the visible light, it casts a shadow. So it stops the photons. So some energy passes through it, some energy stops. So everything has a stopping, collecting capacity. So depending upon that, one telescope has particular material which can detect the far UV photons. The other one can collect the near UV photons, but that one has a splitter. Like if I want to detect as well as see, what will you do? Light is coming, I can put a 45-degree mirror. Some part of it comes to, some reflects to that. So there's a splitter which splits the beam. Like if there's a camera out there, I want the light to be detected, but I want to also see what's being photographed. What do I do? I split the beam which is coming in so that I can see through the side and detect it. So this is exactly what it does. So the thing which is split, near UV goes, and then you can see the visible. So visible and near UV is basically the energy of the photon. It changes. Why is the difference? That is the difference at which our atmosphere stops the photons coming to the Earth. You know UV is not entering the Earth's atmosphere, right? The ozone layer protects it. So anything beyond in UV, near UV, far UV, everything is stopped by atmospheric layer. That is the reason why we cannot put ASTROSAT right here to get the photons detected. Why are we sending it up all the way up to 650 kilometers? So we cannot detect these photons right here. The atmosphere blocks everything. So all these are happening above the atmosphere. So that's why we need space.
Why the life of ASTROSAT is limited only to 5 years?
When it is say 5 years, it's called nominal life. So that means minimum you expect the satellite to be alive for 5 years, but it can go for 10 years easily. So as you can also see that, Mars mission as well, whatever was expected, it has gone much, much beyond that. So there are many more missions like that. Yeah, Rakesh want to add.
So what happens is you have this thrusters here. See, the satellite has to be fixed in an orbit, right? It shouldn't drift away. But in reality, it will slowly drift away due to various gravitational influence and fluctuations. So the fuel is added in it for the thrusters. So for a nominal operation where once in a while you have to correct the orbit, and they calculate the rate of it. Based on that, we say it is 5 years. But in reality, you may not need to correct it that often. In that case, it might go on. The instruments itself has much higher lifetime, so that shouldn't be a problem. Most of the time, satellites, the lifetime is decided by the fuel on board. How far you can keep it in orbit.
Why can't we observe the sun with ASTROSAT?
The instruments that we have on board the UVIT are extraordinarily sensitive and are meant for low fluxes. We cannot afford to focus them on the sun because our detectors would be destroyed immediately. So no, we will not be getting solar data from UVIT or indeed from any of the X-ray missions.
I mean, you had a question about this, chances of meteor shower or something destroying. You see, first of all, something to hit in a space, in three-dimensional space, probably the chance factor is 1 in billion. And these particles, they may, attack the solar panels. That can get damaged. So we'll have, in that kind of circumstances, we'll have power issues and so on. There is a normal degradation of instrument detectors and so on and so forth. So even if, as Rakesh was trying to point out, apart from the fuel, also one needs to worry about the degradation of, instruments with time. So it's much beyond 5 years normally. We have satellites which we are working for last 20 years, which nominal life was given as 5 years. So.
Finish up on the meteor shower thing. It has to be noted, besides a low probability of interaction, there is a finite and not very low probability of micrometeorite hitting your sensitive instruments. But this is a problem faced by all space instruments. There's also a question of a lot of space junk which is floating around. That is also a problem that is faced by all space instruments. And that has to be tackled with. We cannot afford to not send up missions just because there's junk floating around or because of micrometeorites. Okay?
When do we get the first light? What will be the object?
As we said, a first light of each instrument is different. Every instrument has its own schedule for opening up. That's basically because of this UV is got very strict contamination. Why doesn't the UV come down to Earth? It stops by the atmospheric. Molecular absorption is very high, right? So you can't say that just contamination free. It's a molecular contamination free. The molecules absorb the UV. So you have to get rid of the molecules. So how do you stop the molecules? To get this instrument itself is a big, very, very challenging system. You need clean rooms and molecular less rooms and things like that. Now, when these instruments open up, they can outgas. So we don't want these things to go and contaminate. So each instrument has its own requirements. As I said, it's a complicated system. So just one means you can just have your plan and execute it. It's like living in a community, right? So we are living in diversity. So we need to make sure that everybody coexists. So it's just a plan like that. So you have different instruments coming on at different times so that it doesn't contaminate the other. And at last, UVIT doors will open. So that time, we are planning to have co-aligned instrument and observation of some specific targets, which will tell you, okay, this is the multi-wavelength mission, and these are the specific things which are being looked at to demonstrate the full capability. Till then, for about 150 to 160 days, only one instrument at a time will come on and observe. After 160 days, everything will come and observe together. So we have some time slot to demonstrate this capability. So that probably is the first light of the ASTROSAT itself.
Most common first light targets will be the Crab Nebula, which is a nearby pulsar with its own supernova remnant surrounding it. And it's a very important object for all X-ray instruments because that is how they check that their fluxes are as they expected in the laboratory. So it will be their calibration target, and that will be their first light calibration target. We have a range of standard stars, stellar objects, not pulsars, but very bright known fluxes in UV, and we will be using those for our first light objects. And then, of course, when we come together, there will be another series of objects, not necessarily all visible in every wavelength, but every one of them important and asking several fundamental questions about the nature of physical nature of emission of that wave band. Okay?
Is it possible to observe an object for long duration? How will the tracking be taken care of?
Yes, provided you don't end up destroying the instrument. It's very necessary to realize that every instrument has its own sensitivity limits, and you will not necessarily look at one object in all instruments. The duration of the orbit itself is 90 minutes, and if you fulfill all requirements, that is to say you are always 90 degrees away from the sun, 12 minutes away from the moon, in that case you will be able to see it for the full 90 minutes. But there'll be very, very few UV objects that will ever fulfill that requirement. So most of our UV observations will take place for at the most 45 minutes or so per orbit. The X-ray instruments, of course, will have their own requirement. We will combine orbits, yes, thank you. We will be combining orbits. It's obvious that just because you cannot see the object completely in one orbit, that doesn't mean that you will not go back in this next orbit and look at it again. We will, because the one advantage of being a part of an instrument like this is that you can go back and take a look at objects that may have been even observed earlier by other instruments and take long duration observations, very deep observations, very sensitive observations. You're probing the nature of matter, you're probing the nature of stars, you're probing them in extreme wavelengths, sometimes in wavelengths that haven't been looked at before, and you'll also be probing them at extremely short time scales, and you'll be probing them down to very low sensitivities, very low fluxes. That's the advantage of ASTROSAT.
The most important thing to remind you is that the UVI telescope is much superior to many other missions which are done in the past. So for example, the GALAX mission which NASA sent, which is already over by 2009, it was decommissioned. That was having a resolution of 6 arcsecond. I mean to say that you can resolve two objects, 6 arcsecond separate. But with the UVIT, you can do it 1.8, so it's something like 3 times better than any other previous mission. So obviously we can resolve the auroral regions of gaseous planets in our solar system. But we need to deal with the tracking which is different than the normal stellar sources. So that's one thing we are planning.
India is a poor country. When people are dying for food and water, should we be spending money on projects like ASTROSAT?
All engineers, all technicians working in ASTROSAT, in ISRO, in IAEA, all Indian institutions have the greatest of sympathy for anyone who has had to forego a basic meal or basic human requirements in order to live their day-to-day lives. We deeply sympathize with anyone who has who's poor. We understand that a certain amount that India is making sacrifices in order to do something as basic science. But basic science is indeed fundamental. It's very important in the long run to a society. A society which says it can afford to do basic sciences is saying that it can come together as a society. You can come together as a people. You can do things, abstract things, not necessarily the most crucial, important day-to-day things, but things that are important for your future. It is to be noted that with the advent of ISRO, with the advent of research institutions, with the advent of universities and places of higher learning, India has put a foot forward and is saying that our next generation will have a better life. We will give the intelligent young people in this country a chance to stay back, to work on their dreams, to look at something different, to do it even if it is abstract, even if we cannot really afford to pay sometimes for our day-to-day amenities. It's a huge sacrifice Indian people are making, there's no doubt about it. We have great sympathy for them, but we think that to some extent, to the extent that we can afford to pay for it, we should invest in fundamental sciences. It will come to use to us, not in this generation, but certainly to the next generations onwards.
See, you have this mobile phone. Everybody has a camera sitting on that, right? Now everybody uses a mobile with, nobody has a mobile without a camera, right? So where does this actually start? This camera stuff. This is a charge coupled device. This is all state camera. It is very cheap now. But 20, 30 years back, it was not cheap. Where did it start? It started with trying to detect photons like this very low level light, very low level astronomical purposes. Cameras for that. very low light level collection cameras. And that was the time when astronomy was changing from photographic plate to digitized observation. Now then the production became so much that, industrialized the whole thing. Now the cameras are very, very cheap. In every mobile camera it is there. So you have to start some requirement which is very stringent. And that basically comes from basic sciences. And so many applications in medicines, medical applications. So these stringent criteria do not come from daily life. These stringent criteria come from these extreme science cases. So this pushes you hard to devise a thing, which is in normal circumstances, if you have just 3 meals a day, then you don't want to think about it, right? So this thinking can produce a radical change in lifestyles, changes in various stuff, health, conditions, and warning systems. So all these kind of things are driven by these extreme science cases. So that's why science plays a role.
I'm very happy that you all came up with very interesting questions. I thank all the press members, students and enthusiasts for making this a very enlightening press meet. I also take this opportunity to thank all the team members from the Indian Institute of Astrophysics for having answered all the questions and quenching our thirst for knowledge. Thank you.
Yeah, I would just like to add from the Astronomical Society of India, as I mentioned in my first comment, that I would like to thank Shailaja also. She is also part of this public outreach committee, and she has organized this in Bangalore. So parallelly in Bombay and Pune, this event is being taking place now. So if you have any questions in terms of ASI or ASI's public outreach, please do not hesitate to look at your website as well.